Swayam Prabha. Digital India. Educated India.
So I'm here to talk about something you might say, this is very ordinary. Water, what is there to talk about water? I would like to begin by asking you a question. What do you think is the most exciting topic in science? Or not limited by what you read in your textbooks, but in the world around you. What do you think is the most exciting thing? Dark matter? Quantum mechanics? Anything else? Anything else? Okay. Yeah. So the most exciting thing, according to me, is we ourselves. How our body functions, how our mind functions, our consciousness functions. Science is barely able to probe these things. And it's omnipresent. We are always carrying ourselves with us all the time. We don't notice how significant or how interesting that is. In the same way, if you look at materials, there are so many complicated materials, and then there is water. It is there everywhere. There is a famous lines from a poem, go, water, water everywhere, not a drop to drink. We'll come to that later. So water being everywhere, we feel this is something people should have known since a long, long time. What is there to know about water? So what I will cover in the next couple of hours these are the topics I'll discuss. Some historical and modern day mysteries about water, and then what is the glue that binds water that is very special. Some mysteries which were solved along the way, such as the configurational entropy of ice, and some unique properties it possesses, like high dielectric constant and why salt dissolves in water. At the end, I'll touch upon what new things we are trying to find about water and what the future implications would be. So let's look at historical and modern day mysteries, and I'll begin, of course, with historical ones. Water has formed a central part of human thought. Thousands of years back, people have thought about water, and here is something to flash about that. Aristotle, 400 BC, he came up with this classification that all material are made up of 4 things. What are those 4 elements? Quote unquote elements. As you know, the elements are those in the periodic table, but that's what came much later on. 400 BC is really long time ago, and these were the 4 elements: water, air, fire, and earth. And you can see water has been given so much prominence. It is one of the 4. It might appear why anybody should have such a classification, but if you do not know the chemical composition or the chemistry, then it's based on the physical appearance of the solid or the liquid or whatever it is. So here, this is something liquid-like, this is solid-like, this is something which is hot and difficult to understand, and then you have air, transparent, pervading everywhere, weightless. Plato had a slightly different one, and he added one more to the list, that was ether. These 4. So why does water play such an important role? I'll just dwell upon in the human consciousness why it was so important. But the view today is the following. You have water, which is basically a liquid. You take that liquid, solidify it, it becomes ice. You vaporize it, evaporate it, it becomes gas. We know this because we know the microscopics. The same molecule is converting to this and that. But then, in the time of ancient Greece, water did not convert to water vapor. How do you know it's the same thing? Water converted as a water to air. That's the transformation. And water to earth when it solidified. They didn't know it's the same substance, because they could not distinguish the chemistry from the physics. The physics says the water has become earth, the water has become air. ice, liquid water and water vapor were not known as the same substance. They appeared like they were different substances. And then with the combination of these, all matter could be thought of made up of these four. So this transformation properties of water are really unique. There is no material which undergoes so much dramatic transformations. So much that Thales of Ionia, again in ancient Greece, he said water is the basis for all matter, because water could be converted to air, water could be converted to earth, and water puts out fire. So it is connected to all the other elements. And so it should be the basis for all. It's a special one, the one at the bottom of the square. It's a special one. And all reality, according to him, was derived from a single elemental substance, water. This may be wrong from today's perspective, but this idea laid the foundation that there is something elemental constituent of matter, that atoms eventually make up matter. How did this idea originate? This idea originated from Thales of Ionia, who said water is the basis for all matter. Later it changed to atoms are basis of all matter. And then also coming to Indian literature, you find the creation hymn in Rig Veda, which also mentions, was the universe composed of water in the beginning? There was only water everywhere. And it's a very beautiful lines you can find, translation by Griffith, the Nasadiya Sukt. I'll just mention so that you can read at a later time. This was from the ancient world, but let's see the Renaissance age mysteries. Modern science evolved in Europe, and what were the mysteries about water that people knew at that time? One question which was asked, where does the water in the rivers come from? So Ecclesiastes says all the rivers run into the sea. Continuously the rivers are running into the sea. The sea is not getting full. It can take more and more, and that appeared like a mystery. And the famous Leonardo da Vinci, he makes the following observation. There is some kind of a cyclic process, and water passes from rivers to sea, sea to rivers, back again, and it makes the same round such that, look at the beauty of this, all the sea and rivers have passed through the mouth of the Nile an infinite number of times. It's the same water getting circulated, the water of the seas and the water of the rivers, everything has at least passed the mouth of the Nile, not once, but infinite number of times. That's what he speculated. And the hydrological cycle, something you would have studied from class 3, it appears like, okay, this everybody knows. But people didn't know about it till 1500. So Leonardo da Vinci had the following idea. It was not clear where this water in the river comes from. So maybe there is a connection between the sea and the heating of the earth takes the water back to the rivers, and it flows from the rivers to the sea. This was an extra component in the hydrological cycle people didn't know about. And then it took an interesting experiment by Pierre Perrault, which is known to be the first ever quantitative estimate of earth science. Earth science is today a discipline. People like to study climate, earth, geology. So the first quantitative estimate was done by this person and written in this book, The Origin of Springs. He experimentally measured the amount of rain falling in a certain area, a catchment area in France. He went to different locations, studied for the whole year how much rain fell in different places. Then he added that up and said the amount of rain that falls is 5 times the amount which flows in the river. So obviously the rain is responsible for the water in the river. This is how they concluded in 1674. And this is then the hydrological cycle as we know today appears something very simple. There is evaporation, precipitation, plants are leaving water up there, sea is evaporating water, then there is rainfall, runoff through the rivers and back to the sea. Even then, I'm sure you would have not noticed some of these aspects. I'll just point out this picture. The hydrological cycle is an extremely complex thing because it has cogs turning at many different speeds. This is just a graphical representation of that idea that hydrological cycle is not associated with any one speed. There are so many different things happening. For instance, when water evaporates from the sea, eventually it rains. How long does it take? When the water from the river goes to the sea, how long does that take? Then there is melting of ice, and then there is the ice ages. Let me get some answers. What do you think, how long it takes on the average for the water to evaporate from the sea and then come down as rainfall? That is, how fast is this gear turning? Any guess? A week, right? And how about the next one? River source to the sea? Weeks. Okay, very good. Actually, good answers. So it takes 10 days for the first one, a few weeks for the next. Glaciers are melting at few kilometers per decade. Ice ages happen at 20,000 years. And then everything works at the end to maintain a kind of equilibrium, though all these gears are rotating at different speeds. So that's why the hydrological cycle or the water cycle is extremely complex. And this has led to a hypothesis. It's only a hypothesis, it's not accepted by science, by James Lovelock, who said the earth is self-regulating. Though so many things are happening, it keeps maintaining conditions that life can go on. So what are some modern day mysteries about science? This was the historical perspective. So many interesting things happened during ancient times and the Renaissance period. Modern day mysteries, water being so crucial to life, but if I were to extrapolate, take the hydride series, telluride, selenide, sulfur, oxygen, they are all in the one column of the periodic table. If I didn't know about water and if I just extrapolate, which means take the information and extend it, this is a plot of the temperature for boiling and melting of these different hydrides. This boils around 0 degrees C and melts at some negative temperature, and then it goes on decreasing such that water should have existed as a gas at room temperature and pressure, but it does not. Thanks to that, we have life. Why is water breaking this rule which you observe for the other systems? Yeah.
The high electronegativity of oxygen and non-linear structure to your molecules, it gives a dipole moment, hydrogen bonding, and
right.
polar.
Yes, we will discuss that in more detail. Yeah. So had it been the case that water was in a gaseous state, then the earth might have been something similar to Venus. It would have an atmosphere which is cloudy, not of sulfur and methane, but it would have water vapor as one of the important constituents. All the water from the oceans would have been in the vapor state. So one of the modern day anomalies, modern day mysteries, I'll show you why this is a mystery. Maybe the textbooks tell you there is an explanation, but I'll show you that there is no clear explanation. Water has a density maxima at 4 degrees C. You take water and start cooling. You take a metal or most solids, you start cooling them, they'll contract. They'll occupy lesser and lesser space as you cool down because the atoms are not vibrating so much. And then here, that is what is happening. It's becoming denser, fine. It reaches a maxima and then starts decreasing. It has a peak at 4 degrees C. And then when it becomes ice, we all know ice is lighter than water. Very unusual. Most other cases you would find that the solid is denser, the liquid is less dense. But here you have the converse. A normal liquid would behave as follows, whereas water behaves as. So this is one anomaly about water. There are many others. There is minimum isothermal compressibility. Isothermal compressibility, isothermal means at a fixed temperature. how much is the compressibility, is the ability when you apply pressure, how much there is a change in the volume. That shows a minima at 46 degrees C here for water, whereas for a normal liquid it should be just a monotonic dependence. Then the specific heat at constant pressure, Cp, yet a different temperature, 35 degrees C, it has a minima, whereas for normal liquid it just has a monotonic dependence. So not just that there is one anomaly at 4 degrees C, there are so many anomalies and so many temperatures, and we have to account for all of them in a single model. So let's look at the most popular one. You must have noticed in your glass when you put ice, it floats. What if water were a normal liquid? It were not like other liquids. Then if you look at some lake or pond, as things freeze at the top, because the top is one which is exposed to the atmosphere, it's getting cold because the outside is cold, the ice which will form will go and sink at the bottom. And this, it would start growing from the bottom. There will be ice, coldest part at the bottom, it's the heaviest thing. This, if it were a normal liquid, it doesn't happen. What happens is that ice forms a layer at the top. And the process is actually very complicated. It involves convection, that is, the 4 degrees C is the densest water, that by convection comes down, and a layer of cooler water which is lighter lies at the top, and then that starts freezing at the top. So you have lakes, even oceans covered at the top, such as pictures like this, polar bear at the seal hole. And lakes also freeze at the top. In northern countries, people do ice skating on them. How do we understand this particular anomaly is what I would like to discuss next. And then there are these 3 states of matter, solid, liquid and gas. There are different ways of defining them, but maybe I would like to know what you think are the distinguishing features of solid, liquid and gas, right? So in terms of shape and volume, one can define the 3. Microscopically, of course, there is going to be a big confusion. There is another definition? Shear, in terms of liquids and solids, you can discuss shear will cause the liquid to flow, shear will cause the solid to deform. In what way are they different?
Well, in solid, they only have vibrational motion, whereas in liquid and gas, they have various.
So very, very nice answers from all of you. Your good name is? So he gave an answer in terms of the physics, in the sense how the appearance looks like, the shape, the volume, whereas your answer is in terms of the molecular structure, the macroscopic answer from you. That we can come a bit later. It's getting, because all liquids may or may not have van der Waals forces. Right? So if you look at this, the distinction between solid and gas is very clear. There is no doubt about it. Solid will not expand to fill up the space, and then in terms of physical macroscopic properties, they are so different. Even microscopically, the atoms are very close to each other. They form a regular array. Gas is totally different. The distinction between liquid and gas is a little subtle. When do you say this liquid and gas are different? Because pictorially, here they look the same. It's just that I put them a little apart. When they will suddenly become a gas, that is a question to answer. Don't worry about the schematic diagram. I could have said this is liquid and gas, drawn something and say that is a gas. So what do you think is a distinguishing microscopic picture of liquid and gas? Density, but there is no absolute number. There are liquids with different densities, there are gases with different densities. You can compress a gas and make it denser. So what exactly is the point? At this point, the liquid is not a gas, the gas becomes a liquid. Some transition point. Agree, but that's a macroscopic definition, right? You can put it, and now in terms of this kind of microscopic picture of atoms or molecules moving around, what would be a distinguishing feature of liquid and gas? What should it be? The problem with that kind of definition, it doesn't even work for solid to liquid for ice. So the distance should probably be growing, but it actually decreases. Very close answer. But now we would like to talk of them as separate things. What is a liquid when it becomes a gas? Because interface is more complex. You're looking at how together they interact, but I'm looking at them separately when one becomes the other. A bit louder, yeah.
The entropy in the movement.
Entropy of the
Gases tend to have more entropy in other
more and
molecules
less
than
is very
it's
qualitative.
but
So we have to
you
get
can
quantitative
quantify
when it comes to. Okay, let's move on. So qualitatively, I can say many things. Mobile particles, more mobile particles, and this is a dense periodic frozen arrangement is a solid, and liquid is mobile, gas is much more mobile, and it's still qualitative. I need to get a little more quantitative. So then I could make plots, and the plots are made as follows. Imagine you are one atom or one molecule in a solid, and then you go on searching for neighbors. Then you will have a plot of density keeping one of the atoms as the center. What is the density at a certain distance? The density will be very high in the beginning because that's your own density at the origin. Then at very fixed distances, you will encounter the next sphere, the next sphere. You can average. For instance, if I go along certain direction, there will be no sphere. Certain direction, there will be a sphere. I can do an averaging for that distance r over a sphere of radius r. So I'll get a spike. Then another spike for the next nearest neighbor, another spike, and so on. These spikes will continue all the way to infinity. Whereas for a gas, you will have something, a large density, because that's yourself. After that, this is a very small density all the way to infinity, almost close to zero, because you rarely encounter anything. That's how it goes. It's not exactly zero, but the density is really small. What about liquid? It has to now microscopically get distinguished. Do you think the liquid would look like this or like this? Or would it be different from both? I'll come to that. Maybe we can answer this one. And, you think it will be closer to the gas, and this part, this value would be higher.
Yeah.
Right. Okay. So one could imagine sitting in a tiny spacecraft and having a camera and taking pictures around you. You are sitting on top of a single liquid molecule. Occasionally you will photograph something, and other times you would not. If you then average out, you will see that there are concentric rings forming, a few of them, not many, because there is a certain repulsive force. If not anything else, then there is this repulsion coming called as hard sphere repulsion. The liquid molecule has a certain, if you treat it like a sphere, then the adjacent sphere cannot enter that. There is impenetrability. So this is what is known as short range order. There are weak attractive forces, but most importantly there are repulsive forces. And these are not so important in the gas, because the gas, their molecules are so far apart, you may or may not even consider the existence of attractive and repulsive forces. But in a liquid, they are relevant, especially the repulsive forces are relevant, and they create what is known as short range order. So the graph for a liquid would be midway of both. It will be neither this nor that. Short range order, some peaks, as your good name? Adi just mentioned. So it has some oscillations, but not all the way to infinity, and then it reaches some low average value at far off distance. And these are not just theoretical ideas. So there are experiments based on diffraction, where people use neutron diffraction, they can obtain all these plots. And this is where there is a clear distinction between a liquid, a gas, and a solid using microscopics. So then what really is the distinction between liquid and gas? I'll explain a little more about the same thing. I'm sure all of you have learnt long ago about the ideal gas law. Boyle's law, Charles' law, right? In a gas, the product of, if your temperature is constant, the product of pressure into volume is constant, or in general, PV is equal to nRT. Pressure is more, the volume will be less at a given temperature. Then van der Waals came with the correction, because PV is equal to nRT was not able to explain the isotherms of all the gases. He came up with this correction. One part of the correction was related to the weak attraction between particles. Another part was repulsion, the volume occupied by the particles means they can't penetrate each other. So that's a kind of a hard sphere repulsion. So there is attraction and repulsion built into his model. One term added here, one term subtracted there. And with this, he could then get isotherms for various real gases at very large temperature, far away from the melting temperature. Boyle's law is indeed valid, PV is constant for the isotherm. But as you are coming closer and closer to the temperature where there is a transition from liquid to gas, sorry, I said melting, I should have said vaporization, the vaporization temperature. Then the isotherms, that is plot of PV at a constant T, keeps on changing, and then you have a region where, okay, don't worry about this shape because van der Waals could not exactly explain the real isotherms, but there is a sharp decrease in the volume at a given pressure. That is the process of liquefaction. A gas converting to a liquid, that is at a fixed pressure, the volume has completely decreased. And then on this side, at a fixed volume, the pressure, if you try and change the pressure, the volume changes very less. That's the property of an incompressible liquid. So both of these are built, and van der Waals was just able to touch the surface of the problem, how a liquid forms from a gas. So the same idea can be extended now to microscopic, saying that whatever correction van der Waals had given, which is a combination of attraction and repulsion, become relevant for the liquid, and that is the distinguishing feature between a liquid and a gas. How normal liquids should be understood, and someone here just said van der Waals, I don't remember who, maybe you can raise your hand. Yeah, yes. You said about van der Waals, and I just described van der Waals correction leading to liquefaction. A liquid should be thought of gas plus van der Waals correction and lowering the temperature leading to liquefaction. So the perspective for understanding a liquid should be this way. Going from gas to liquid, they see increased density, then they start seeing repulsive forces, and then there is also weak attraction. The weak attraction is the van der Waals attraction, the quantum mechanical effect. However, water is not understood in the same way because of this density anomaly, ice being lighter, less denser than water, which forms from the melting, which means some aspect of ice is preserved in water. The perspective for ice, or the perspective for liquid water, should be going from solid to liquid, not going from gas to liquid, because it shares some property. Something should have been there in the solid which is still there in the liquid. Otherwise, it can't have a density which is more than the solid. That's the reason why, from a microscopic perspective, water is so different from all other liquids. The very fundamental approach is not going from gas to liquid and looking at liquefaction, but rather looking from solid to liquid and then looking at melting. So then you have probably studied some phase diagrams, right? Are they part of your 11th, 12th syllabus? So this is, for instance, phase diagram of CO2, and it has regions, which you can think of solid land, like borders, one country called solid land, another called gas land and liquid land. And then there are these strange countries whose borders just stop at a point. After that, people here belong to the same nation. But here there is a distinction, liquid land and gas land. This is the critical point. And this is a plot of pressure with temperature. One also makes pressure, temperature and volume, but I've just taken one slice of that. We can see some of the things here on this plot. For instance, going at a fixed pressure, one can go increase the temperature, the solid would melt and give you the liquid, or At very low temperatures, the solid can directly give you the gas, so that is sublimation. Coexistence of all three is the triple point. Liquid, if the temperature increases, it evaporates, that is evaporation. And then beyond the critical point, you could go from the liquid to the gas in a continuous way. It's very hard to say what is what. Things are becoming fuzzy out there. Then the important thing is the latent heat at these points. When you make a transition, you pay some toll. You get back the toll fee when you come back. How do we connect all this with some day-to-day observations? So one of them is that this is pressure, this is temperature. If I decrease the pressure from the atmospheric pressure, then the liquid to gas transition, if this was for water, happens at a lower temperature. And the practical consequences, people in Tibet, they boil their tea, but the tea is not at 100 degree. It boils much lower, as you can see here. So the culture in Tibet is not to sip tea, but to gulp tea. You can observe, maybe the Dalai Lama does it frequently, gulping tea, which puts him in trouble because he travels all over the world. Another different aspect is this line for carbon dioxide. It was going north-north, well, that is east, north-northeast, and this goes north-northwest. It's unique only for water, that is the solid liquid line has a different slope, and the origin of that is related to the fact that the ice is less dense. One other thing is, if you ever happen to, well, go to Mount Everest or something close, anyone has climbed up high peaks here? Which is the highest peak you have gone to? How high was that? 13,000 feet. Fine. So if you happen to go to a really high peak, you could test out this experiment, cooking eggs, which is also related to the fact that the boiling happens in water at much lower temperature. So this is a series of experiments done close to Mount Everest. The white cooks at 85, the yolk cooks at 65, water boils at 70 degree on Mount Everest. So you will have only the yolk cooked and the white will still be in the raw state. So all these are consequences of. But then there are many other interesting things happening. The phase diagram contains much more interesting information which is not evident. Water can be superheated and supercooled. And this is something I'll just mention without discussing the detail. We think liquid water exists from 0 to 100, but you could even take it under some conditions beyond 100. You could even take it to some conditions as low as minus 140 C. You could have liquid water. And the really puzzling thing that scientists are trying to look at is called no man's land. What is this no man's land? It's actually no man's water. Minus 45 to minus 120 is an interval where it is impossible to have liquid water under any conditions. Then again at minus 120 to minus 140, you can have liquid water. This liquid water, how do you produce this? You have to produce amorphous ice. And amorphous ice melts at minus 140. So minus 140 to minus 120, it will be in that state. Then you could also go your regular water, you can cool it down, you can super cool it by providing the right conditions. And this, as you can see, so many question marks. So these are topics for research. People still don't know why there is something like a no man's land. One would assume there will be a continuous series of temperatures where water will exist. Exist, doesn't exist, exist again, which is extremely puzzling. So an analogy, so if a foreigner was asked, go around the country to find out, sorry for the spelling here, go around the country to find out how people in India live. So what the person does, he visits the house of the Prime Minister and then makes all the notes saying, okay, this is how people in the country live, but knowing about that doesn't tell us about how the country lives, right? Similarly, knowing about water, though so much research is happening about water, will not tell us anything about other liquids. They are so extremely different. Water research is a discipline in itself, because there are no other liquids which are like water. I said there is a connection between water and ice, and let's look at that connection in more detail. Water H2O, right? Oxygen with 2 hydrogen atoms, which is bent. So one question is why the molecule is bent, and it is bent at an angle of 104.5 degrees. So why is the angle 104.5? So actually the structure should be shown in this way, that there is also the lone pair of electrons with the oxygen. They are all lying, because they don't like each other, they are lying on vertices of a tetrahedral. The coordination is tetrahedral. The oxygen lying in the center, and the angle for a regular tetrahedral coordination should be 109.5, which is the angle taken by methane. But here the repulsion between the lone pairs is much more, and that causes the bending to become a little more, and the angle changes from 109.5 to 104.5. This is one of the representations of water. This is ideal, so don't believe this. This is actual, closer to actual, but nobody knows what is actual. Oxygen in the center, again tetrahedral coordination. This is hydrogen and hydrogen. They have slight positive charge because of the difference in the electronegativity. And these are the lone pairs, but the lone pairs are a little closer. They are not really at the same distance as the hydrogen. This is called TIP5P water. You might wonder where I can buy that. TIP5P water is available in all supermarkets. You can buy it. It's the same water that we drink. It is one of the models of water, one of the 50 plus electrostatic models of water. People have come up with so many models, because not even one model is successful in explaining all the anomalous properties of water. So something can explain the minima of specific heat, something can explain density anomaly, but not the minima of specific heat. What can explain the most number, but definitely not all, is TIP5P water. It can explain many, but not all unusual properties of water. Why is it that there is not a single electrostatic model till today which can explain water? The reason is that the problem with the word static. We think that this configuration should explain, but things are dynamic in water. Hydrogen bonds are breaking and forming, the molecules are moving, and the trouble is with the question itself, why should there be any static model to explain water? As one of you already pointed out, the second part, the glue that binds water, is the hydrogen bond, and we should understand water from ice, going from ice to water. So this is the tetrahedral coordination showing your water molecules. The oxygens are at these places, at the corners, and the hydrogens are shown here. The solid line is the oxygen hydrogen bond of the water molecule, whereas the dashed line here is the hydrogen bond. Now, what exactly is hydrogen bond? We'll just spend a little time, but it was really mysterious. People were not willing to accept the hydrogen, which has only one electron. How can it bind to two different atoms? It took a very long time for people to accept this idea. Something with only one electron can bind to. Binding to oxygen is all right, but then it gives a lot of charge to oxygen. It sits with a positive delta charge. Oxygen has a negative delta charge. And then the second bond is electrostatic in nature. Let's skip this. You have one water molecule shown here, H2O, and delta plus charge on H, delta minus charge on oxygen. Then there is a neighboring water molecule which comes closer. Why should it form a second bond? That is purely electrostatic. You have a charge and a dipole, or maybe a dipole and a dipole, or a charge and a charge. So many combinations are possible. In fact, one can look at all possibilities. Is it charge with charge, charge with dipole, dipole with dipole? Dipole, as you know, is separation of plus and minus charge. They have different dependencies for the potential. For charge, it is 1 by r. For charge, for charge dipole it is 1 by r square, for dipole it is 1 by r cube, and so on. People have theoretically looked at the properties of water considering different interactions, and they could show that it's not dipole because that's very, very weak. It's common to many systems wherever there is a dipole. Actually, it is energetics is closer to a charge dipole interaction, and the reason this happens only in water is the small size of proton. The proton can come very, very close to the neighboring water molecule, and then it can interact with the dipole of that water molecule and have a charge dipole interaction. Had it been far away, we would have thought of it like a dipole interaction, which is weak. The fact that it can come close enough and have this strong interaction creates this unique thing called hydrogen bond. There is no other bond named after any other element, only hydrogen bond is the different one. And some idea about the numbers. So this is the fractional charge on a water on the hydrogen. It's not plus 1 e, it's 0.24 e, like fraction. If you consider a individual water molecule H2O, then the OH bond distance is about 1 angstrom or 0.1 nanometer. Whereas if you take free oxygen and free hydrogen and bring them together, that distance is 0.26 nanometer. It's a van der Waal, sum of the van der Waal radii. In case of this hydrogen bond, the distance is intermediate to both. It's not as close as the OH distance in H2O, but it's also not as far apart as a free oxygen, free hydrogen without reacting. You add up their radii, that's too far away. Then let's see the picture, the reason why the density is more for water than for ice. Again, this is one of the many explanations, but I'll just start with this. In ice, you can see from this picture, every water molecule has 4 neighbors, and it's fixed, 4 nearest neighbors, and also it has 4 hydrogen bonds for each oxygen, for each molecule, not each oxygen. Each molecule has 4 hydrogen bonds. Because there are 4 neighbors, each neighbor has a hydrogen bond. In water, the number of nearest neighbors goes up because water molecules are mobile, they are not fixed on that lattice. They can come closer, they can form additional kind of interactions not present in ice. So their average number of nearest neighbors is 5, but not all are forming hydrogen bonds, so number of hydrogen bonds is only 3.5. What determines the density is the number of nearest neighbors, and therefore the density of water is more than the density of ice. Is that fine? These are very interesting cartoons from the book of Philip Ball. I'll just explain how you could mimic a water molecule, because you have arms and feet. So if you stand with your feet 109 degree apart, 104.5 degree apart, very hard to do, and then your oxygen is like your belly, and raise your hands and turn about the waist by 90 degree, and that is what would form the local structure of the water molecule. And this is, for instance, shown here. This is one water molecule with lone pairs and the hydrogens. This you can think of as hydrogen bonds. The lone pair of the hydrogen bond is made to the lone pair. So the hands are holding the feet, and the structure then builds on from there. You have a 3-dimensional complete network forming as a result. You can imagine the hands to be H2O, and then they grasp the lone pairs of the next water molecule, and in this way, this kind of a 3D structure, of which a 2D projection is shown. Okay, little difficult to appreciate, but I'll just point out that there are hexagonal rings forming as a result of the way this tetrahedral coordination is there and the way this bonding happens. So this is one, and this is the next, and this is the next, third, the fourth, the fifth, and the sixth, and then back. I hope you are able to see this hexagon. And there are these hexagons present in water, 6 atoms forming a ring. In ice, more importantly, because in water it is derived from that. And that is the reason somewhere it is connected. It's not, one can't directly prove it, but the fact that snowflakes are having 6 arms and they have the hexagonal symmetry can be traced to the hexagonal symmetry of molecular arrangement in ice. All snowflakes have this arrangement. And the interesting thing here, Chinese have documented this 2000 years ago. People don't know how. In China, water is, of course, like everywhere else in the world, considered special, but they had the number 6 associated with water. And how could, without having microscopes or anything, they could know about this fact 2000 years ago is also a mystery. The Western world discovered only in 1300 AD that this, when some kind of lenses had been developed, that snowflakes actually have this, universally have a hexagonal symmetry. And then there are these inexhaustible patterns, just like you have in a kaleidoscope. You go on turning, that pattern never repeats. Similarly, for snowflakes, you have hexagonal always, but the patterns go on changing, they don't repeat. This is the ice that I just described, and it is ice 1. But if you apply pressure, imagine all of you are asked to come here and form hexagons, and then slowly we keep adding more chairs to the room. This has few, but then you have to maintain the condition of hexagon. It will result in the situation where hexagons start going into other hexagons, but still preserving because energetically it is favorable to form the hexagon. But if you put them in a smaller volume, then you will have many hexagons penetrating each other, and that is what results in formation of ice 6, ice 7, ice 8, so many kinds of ice. Is also and the amount of pressure needed, well, it's about 20,000 atmospheres, only possible in lab conditions, is equivalent to collecting 40,000 elephants, maybe that's the number we have in India, and putting all of them on a region of 1 square meter. With that amount of pressure, you can convert your regular ice which you have in your fridge to one of these ices, and their properties are very interesting. When it comes to the density anomaly of water, there is an interesting history behind it, of how people try to understand. And I'll just point out a few important models. One of them is that, which is the mixture model of Wilhelm Röntgen in 1892. He pointed out that there could be partial melting. Melting may not be complete. When we say ice has become liquid, maybe there are fragments of ice still floating and some other liquid molecules are there. So that what he called is as partial melting. In his hypothesis, that was the reason why water is so dense. Then there was a cluster model to explain why water is so dense. That is, when it melts, it exists as a few different, so I showed you a hexagon, but maybe a fragment of the hexagon exists, like 2 molecules, 3 molecules holding their hands and then coming closer, and that model was due to Sutherland in 1900. Then there was an interstitial model by this Russian scientist Samoilyov, who said that molecules break and they fill up the interstices, because the structure of hexagonal structure you can see here, it has a lot of void regions. There is nothing here. So the interstitial model involves some molecule breaking and filling up this space and making it more dense. And then there is a uniformist model. And the last one is really radical. It says bonds don't break at all. There is no bond breakage, no bond formation. Whatever is there, but the degree of quote unquote bondedness changes. Bonds are twisting, bonds are, you can allow them to bend, and the uniformist model is very successful to explain many things, by Bernal and Fowler in 1933. These were all analytical models, and people tried to picture what was happening. the story has not ended. So even a few years back, this model came, again inspired by the mixture model of 1892, but this model came only a few years back, and it's now considered to be maybe the right explanation. And this one talks about that the liquid water that you have in your bottle in front of you, you sip it every day, is actually not one liquid but two liquids. And the two liquids, there is a high density liquid and a low density liquid which are coexisting, and that coexistence is necessary to explain the density anomaly. This is still work in progress due to Nielsen. Today, computational tools are available which were not available in the time of 1900s and 1930s or even much later than that. And people look at the process of melting by these computational studies. We have all these rules. There is dynamic structure and two hands. You can hold in water. In ice, one hand can hold 1 feet. In ice, the rule is broken. Two hands can come and hold 1 feet. And you can fill up the voids. You can have dangling bonds, that is, there is a broken arm, there is nothing there. You also have auto dissociation. So in the same structure, you will have all these nice people, hands and feet, but you can have a floating arm or a floating feet in the water. And that the structure created result of that through computer simulations is seen here. It's like a crazy climbing frame, and all of these represent the hydrogen bonds. You can see at some places it is just like ice, other places it is quite random. And then this is coming closer to the one of the analytical models which explains what. Okay, the last thing before we can take a break. I think it's almost 1 hour, right? It's about close to 10 o'clock. Yeah. So then, what am I showing here? IPL auction rules. Okay, before we go to break, let us look at what is happening in IPL. So you see this. IPL rules are so complicated. When they go for auction, the auction itself is something very exciting. People are following which team has got which player, and these are the rules which you can find on the web. Each team is allotted so many budgets. It should have so many batsmen, so many bowler, whom you can release, whom you should not release. What has that to do with? I don't think this is an advertisement for before the break. It's actually related to the study of water. So similarly, in water, it is difficult to predict which hydrogen bond will break and which will form, because both in the IPL auction and water, there is this common concept of cooperativity. The fact that one team will take one player depends on what all other teams are doing. You cannot just look at one team and say this team will do the following. Similarly, in water, the fundamental problem why we cannot explain is cooperativity. We cannot look at one molecule, follow its motion and say this is what will happen, these bonds will break, this is the probability. You have to look at the entire structure of millions of molecules. It's a cooperative process. Only how many teams in IPL are there? About a dozen, right? 10. Okay, I don't watch, so thanks for telling me about 10. But in water, there are thousands and thousands of atoms, maybe millions of atoms. There's cooperation across all of them. So this is the theoretical challenge, cooperativity. You can't tell which bond will break, which will form. I think this is the right point to stop, and we'll take a short break. We'll get back to other interesting properties about water.